In part 3, we're going to explore how to add water across a double bond. So we're going to be adding an H to one side and an OH to the other side. There are 3 different reactions that we are going to use to do this. 2 are Markovnikov and 1 is anti-Markovnikov. And we're going to talk about why we would have 2 that are Markovnikov. All right, so the first one is acid-catalyzed hydration. And this is the reverse of an elimination reaction that you learned at the end of chapter 7, where you used concentrated acid to eliminate water. In this case, you're going to use dilute acid. So you're going to take your double bond and you're going to add, it may say H2SO4, it may say H2SO4 and water. It may also just say H3O plus. You've got to recognize this. This is a dilute acid solution, right? Because H2SO4 is a strong acid. So dissolved in water, that proton is going to be given up, right? What's a strong acid? It's one that dissociates completely, right? It completely gives up that H plus. And if water is around, the water will pick it up. So you just have to be prepared to see either one of these. What you're going to get, oh, no more double bond, is an OH adding to the Markovnikov position, Markovnikov. Right? Eventually I'm going to be shortening this to mark and anti-mark, but for now we'll write it out. The H goes to the side with more H's. The OH goes to the more substituted side. Of course, there was already a proton here. And so there is still a proton here. And there are 2 CH3s on this side. Sorry. Okay, so let's think about the mechanism here. All right, so the mechanism is on this slide. As we are talking about it, we're all going to go let Leroy out. Okay, so the same first step that we saw in the hydrohalogenation will happen in this hydration reaction. The double bond is going to act as a base, right? We have a lot of electron density there. And it's going to pick up a proton from our acid. So we've got that labeled here, right? And it'll leave behind the water. Then once we have the more stable carbocation, the one in the more substituted position. So if we're following along with what I did on this side, let's go ahead and draw that out. We're going to use H3O plus because that's really what's around in a sulfuric acid solution, right? We are going to make the more stable tertiary carbocation. And then we have water, which is a weak nucleophile. We've seen this before, right? This is going to attack that carbocation. Now, there is one extra step that we have to go through here because water has 2 protons. And we can't just pretend that it doesn't, right? We have to do a final proton transfer. Now, what is going to act as a base? We are in an acidic solution. When you are in an acidic solution, do not bring in a strong base. What we are going to use is another molecule of water. Water can act as an acid. It can also act as a base. In this case, it's picking up that proton, giving those electrons back to the oxygen, and leaving us with our Markovnikov alcohol product. This is called acid-catalyzed hydration. And if you recall, probably from Gen Chem, a catalyst not only speeds up a reaction, but it does not get used up in the reaction. So we used the acid in the first step and we got the acid back at the end. So you don't need a lot of acid for this reaction to work, because it is not consumed by the reaction. All right, so we get a proton transfer, nucleophilic attack, proton transfer. This is just the reverse of the acid-catalyzed dehydration. When we had an alcohol in chapter 7, right? This is a chapter 7 reaction here. You used concentrated H2SO4 and you made the double bond and some water. So if you add in more water, this just messes with Le Chatelier's principle. You add in more of what's on this side, it's going to push the reaction in the other direction. So dilute H2SO4 is going to hydrate that double bond. Now, when we think about this acid-catalyzed hydration, we know the regiochemistry is Markovnikov, right? The stereochemistry is the same as what we saw in the halohydrogenation. When you have a carbocation, you can get either stereoisomer, right? The OH can add from the front or the back, so you get a racemic mixture. Most of the time, you're just going to see it drawn as a flat line because it doesn't have a preference. So before we jump into the next reaction, there's a reason why we have a second Markovnikov reaction. There is a carbocation intermediate. And what did we say about carbocation intermediates? When you make them, they can rearrange. So if you have something like this, and you do an acid-catalyzed hydration, right? We use H2SO4 and water. You are likely going to get a rearrangement product, at least a good amount of a rearrangement product. Oh, no. And so if that's what you're going for, great. But what if you wanted the OH to be installed in that secondary position, right? The more substituted side of the double bond, but not rearranged. Well, we have an answer for that. And that is called oxymercuration, demercuration. Oxymercuration, demercuration is a two-step reaction. And this is something that I want you to hear me loud and clear. Some reactions have multiple steps, and it is important that you number them. Some reactions are one step but have multiple reagents, and it's important that you don't number them. When you add in numbers, you're telling a certain story, and we're going to talk about that here. Oxymercuration, demercuration is still a hydration reaction. We're adding OH. It is Markovnikov. So it, in a lot of instances, gives the same product as the acid-catalyzed hydration, but there is no possibility for rearrangement. And so if you have a starting material where rearrangement is possible, but you don't want that, this is a great option for you here. So two things happen. The oxymercuration, where we add in the OH, and then instead of making a carbocation intermediate, we make this alcohol mercury intermediate, and then you just knock the mercury off. So what are those reagents? So let's look at just a simple example here. In step 1, you use mercury acetate, HgOAc2, and water. In the second step, you use sodium borohydride. And yes, you have to memorize all of these reagents. There is a spider diagram up on eCampus that has all of the reactions from this chapter that you need to know. So you can start committing these reagents to memory. All right, so if you see oxymercuration, demercuration reagents, you know that you are going to predict that the alcohol will add to the more substituted side with no rearrangement possibility. I am not expecting you to know this mechanism, but we are going to look at part of it so that you can see why it is Markovnikov and avoids rearrangements. So mercury acetate exists at an equilibrium with this mercuric cation, right? And this is mercury attached to an acetyl group. AC is short for this little CH3 carbonyl. We'll see a lot of that in organic too. Don't worry about memorizing that structure. But the acetyl group is just a little CH3CO double bond. That is going to, instead of the double bond picking up a proton, the double bond is attracted to the mercury, right? So it's just a different electrophile for the double bond to be attracted to. The mercury really doesn't allow the carbocation to form. It makes this little triangular mercurinium ion. That mercurinium ion cannot rearrange. The mercury takes up both carbons until the OH comes on board. And so, if let's, for instance, say we were looking at this example. When we add the mercurinium ion, it's going to attach here. And so no rearrangements are going to happen here. No rearrange. It holds it in place. It kind of reserves the two carbons that were originally in the double bond. From there, the nucleophile, in this case water, will attack the more substituted side. The reason it attacks the more substituted side is because as the bonds are breaking and forming, you get a partial positive on the carbon, and that is going to be more stable on the more substituted carbon. For the same reason, a full positive charge is more stable on a more substituted carbon. And so the nucleophile still adds to the Markovnikov position, but it just didn't have any possibility of rearranging. So my water would come in here and open this up, right? And it would add to the more substituted side. The last step, the sodium borohydride. So if we draw this, now we've added water on this side. We still have our mercury acetate piece. The sodium borohydride comes in and cleans up the rest, right? The sodium borohydride will come in and knock off the mercury acetate piece and replace it with a hydrogen. We absolutely do not need to look at how that happens. So this is the very similar example to what we're doing here. If you want that OH to go to that secondary position, right, it is hard to do that with acid catalyzed hydration because you get both products. When you use oxymercuration, demercuration, look at that yield. 94%, no rearrangements. So it is a more complex reaction to set up. It uses more chemicals, more toxic chemicals. We're bringing mercury in, but it's really effective. If you spend a lot of time and effort making this starting material and you want to put that alcohol in exactly the right place, no rearrangements, it might be worth it to you to use oxymercuration, demercuration. Now on paper, if I ask you how to put an OH in a Markovnikov position, I mean, this reaction works. It does make this product. It just makes more of this product. So let's see, conceptual checkpoint. Okay. We'll just do one more example here. If you had a double bond, here we go. Actually, let's not bring a ring into it just yet. We go, and you wanted to do, sorry, making up problems on the fly is not my strong suit. There we go. Just reiterating, mercury acetate, we're going to work on memorizing that in water, followed by sodium borohydride, will give us the Markovnikov addition of water, putting the OH on the more substituted side, the H on the less substituted side. All right, so we have two ways to do a Markovnikov addition of water, one that avoids rearrangements. But what if I want the OH on the less substituted side? Well, you know that I got something for you there. Next, we're going to look at hydroboration, oxidation. Another two-step reaction. So notice when I say two steps, I'm putting a 1 and a 2. If you don't put the 1 and the 2, that means you're putting all of those things in the same pot at the same time, and that will not have the effect you want. This is another two-step reaction. So I'm going to use that same starting material. Let's say I want that OH now to be on the less substituted side. I am going to start with boron. Now I'm just going to write down BH3, and I'll explain why in a moment. And then I'm going to follow that with peroxide, H2O2. So peroxide, I'm making a mental connection here. Peroxides often lead to anti-Markovnikov products, and I also need a base. I need hydroxide. Now, in step 1, BH3, borane, if you see it with THF is just there to stabilize the BH3. Sometimes you see it, sometimes you don't. Sometimes you'll see B2H6. What I want you to recognize, you need to memorize something so that if I ask you for reagents, you know what to use. I recommend what I've drawn here. But you need to recognize other boron reagents. BH3 forms dimers, and so sometimes it will be written as B2H6, but this is the only reaction that you're going to see boron in. So you need to recognize that boron, followed by peroxide and hydroxide, is going to give the anti-Markovnikov addition of water across a double bond. So again, you are not going to be held responsible for this mechanism, but you are responsible for predicting the products. We are going to take a look at part of the mechanism. Before we do that, because this is the mechanisms help explain why, the hydroboration oxidation adds water, anti-Markovnikov. It also has specific stereochemistry, which we haven't really seen before now. The specific stereochemistry is called a Syn addition. And there is discussion of that in your book around open chains. I will only ever use rings to test your knowledge on Syn versus anti-addition. So this is easiest to see when we are looking at a ring. An asymmetric ring here. We are going to use our borotrihydride there. We're going to follow it up with peroxide and hydroxide. And we are going to take note. Syn addition means, excuse me, that the two things that are added to the same side. So what are the two things that are added? It is an H and an OH. And they are going to go on the same side of that double bond. Excuse me. Dry throat this morning. So if the methyl group is towards us, that means the OH will be going away. As will the other H that was added. Okay, sorry if there's a little blip there. Had to get that coughing under wraps. Okay, so we're looking at this Syn addition, right? This means you have two things to keep in mind. the regiochemistry, which is anti-mark, and that's going to tell you which carbon in the double bond the nucleophile gets added to. So the OH goes to the less substituted side. And then the stereochem, which is the Syn addition, which tells you which face of the double bond the two items are attached to. So the H and the OH are on the same side. So if there was already a methyl group there, it is going to be on the opposite side of the OH. So we don't make a carbocation in this particular mechanism, so there's no rearrangements possible here that we have to worry about. You can see a little bit of information on why sometimes BH3 or B2H6 is written, because when you have the boron trihydride together, sometimes it will form this resonance hybrid, where you wind up getting this these two electrons that are spread all the way across three atoms. THF is a solvent, tetrahydrofuran, that does help to stabilize BH3. So this is a reason why you might see BH3.THF. THF isn't actually the reagent. It is there to stabilize the reagent. So sometimes it's mentioned, sometimes it's not. Don't get hung up on whether or not you see it. You are looking for that boron, right? BH3 or B2H6. The reason that this goes anti-Markovnikov, and again, I'm not going to ask you about this mechanism, but I do want you to see the picture of it because some of us are visual. The boron and the hydrogen add at the same time. And so the way this works, it puts the hydrogen on the more substituted side because in the BH relationship, boron actually is going to add to that less substituted side. It forms this little interesting square transition state. And since they both go on at the same time, it has nothing to do with what makes a more stabilized carbocation. The boron just goes to the more substituted side. Then from there, the H2O2 and the NaOH will go in and knock the BH3 off and replace it with the OH. All this is telling you here is that one boron atom can add 3 different times. At the end of the day, it all gets kicked off. So it's not too much to worry about there. Because the boron and the H go on at the same time, so going back to this picture, this is why it's a Syn addition, because the OH just replaces the boron wherever it is. The boron and the hydrogen going on at the same time, the only possible way for that to happen is for it to be on the same side. Let's see, we're not going to worry about that. This is the whole mechanism for the hydroboration and the oxidation, and it is interesting. And if you are getting into mechanisms, have a field day here. You do not need to know this, right? As long as you know this, the regiochemistry and the stereochemistry. That it is stereospecific. We have talked about this. It is also regiospecific. Now, or regioselective, might I say. I will not ask you to do this on open chain. If I give you something that is open chain, I will be asking you about the regiochemistry, meaning if there is BH3 followed by NaOH and H2O2, they're both in step 2. So if I write them in a separate order, it doesn't matter. They're both in step 2 together. The OH is going to go to the less substituted side. I am not going to make you do this. I'm not going to ask you to put in wedges and dashes unless it's on a ring. All right? It does form chiral centers. You do not need to spend any time thinking about this open chain business. All right, so if we were going to do this practice problem, we aren't touching this methyl group, so it should come towards us no matter what. The OH is going to go to the less substituted side, and it's going to go on the same side as the hydrogen, so that's going to put the OH on the opposite side from this methyl. So let's say it pushes that methyl forward. That means the OH is going to be back. It will also form the stereoisomer here, right? This methyl isn't changing, but it could have also come from the front. So that would have put this methyl back and this OH forward. All right, so you might see either of those products. What's important is the relationship between these two, right? The OH is added to the same side that the H is added to. So that means it's going to be on the opposite side of that methyl group. Either one of these would be correct, and in reality, it would be a mixture of these two. There we go. In this case, a mixture of diastereomers is produced. All right, that is the end of the hydration reaction. So you need to know all three. You need to know the mechanism of the first one, the acid-catalyzed hydration, and you need to know the regiochemistry of all three, whether it's mark or anti-mark. And then you also need to know the stereochemistry, that the hydroboration oxidation is a Syn addition. In the next video, we will continue going through addition reactions.